Yeah, double record.
Excellent. Okay, cool. So, hello, Hamed. How do you pronounce your last name so that I don't butcher it completely?
It's complicated. It's a Pourkhorsandi, but in France they say Pourkhorsandi.
Pourkhorsandi. Okay. So quick introduction. You're a geologist and meteoriticist at University of Brussels, Université Libre de Bruxelles, and you're originally from Iran. Any other interesting facts?
Yeah, I think you mentioned I'm a geologist at the French-speaking University of Brussels. My expertise is cosmic chemistry and geochemistry, which means studying the composition of the chemical composition of rocks. In particular, I'm interested in extraterrestrial rocks, but also I study a lot terrestrial rocks. And but I'm a geology in training, I would say.
Cool. Awesome. We had actually plans originally to speak live at the Icelandic volcano a few weeks ago, but who would have thought that network is pretty patchy in the Icelandic wilderness? I'm actually surprised by how many people, there were people who were on the phone around there. I'd be like around next to the lava and there was a man on the phone with his mom. Just like 100 meters away from this giant eruption of lava. It does feel like we're pretty spoiled now with telecommunications that it would work around a volcano.
Indeed, yeah, it sounds so surreal.
But somehow it did not. I think there was just too much going on when I got there, and so I could only get a couple Instagram lives and couldn't get on the phone with you. So just to catch everyone up who doesn't know about this, hasn't seen my millions of posts about volcanoes. Last year, there was this incredible volcano eruption in Iceland, which was surprisingly accessible. Maybe, I don't know, maybe the most accessible volcano, fresh volcano in the world at that point, at least. Just an hour outside of Reykjavik, and it lasted about 6 months. And then we kind of thought, okay, it's over. And then a new eruption started right around the corner from it this August. And it was funny because everyone was saying, oh, the flow is so important on this one. It's going to last ages. But then it ended up only lasting just a few days short of 3 weeks. I think it lasted about 17 days. And so in Iceland, they've been talking about these events kind of since Fagradalsfjäll, the name of it, last year started. And they're talking about this being a new geological era. And I know that, geological eras can be extremely long, obviously, millions of years. What would this represent? I had heard that this one would be about 2,000 years. What would this kind of represent in terms of a new geological era for Iceland?
When they're talking about the geology of Iceland, especially when we focus on the volcanoes, it's a quite very interesting but extremely complicated volcanic system we have in the Iceland. It's a place that, as you know, volcanoes, they can form in different geological environments. In particular, they're forming in three main regions, we call them, geological regions. One of them is when the plates are going away from each other. So you have the magma just coming up. For instance, what we have in the middle of the ocean, or what we have in the Iceland itself. As you know, it's a continuum of a mid-ocean ridge that we have in the Atlantic. But also we have a type of volcanoes that are forming in places that two plates, they go basically subducted to each other. So they just get closer to each other and then they collide with each other in a very slow time, of course. And also there you have a magma production.
Right.
But also the other one is that you have a hotspot that is forming volcanoes, for instance, the case that we have in Hawaii. But what we have about Icelandic volcanoes is that it's a place that basically you have an area that you have a divergent plate area that you have the magma coming up. At the same time, you have a hot spot. So it's complicating the thing. So you have at least two reasons for magma production in Iceland. And when these guys, they interact with each other, it means that we already know how complicated it is to understand volcanic systems, how the magma is moving beneath the surface of the earth. But when two main processes, they come together, basically it gets even more complicated. That's why as well, for instance, in the case of Iceland, it is very complicated how to predict the volcano. We can even predict the volcano right now with using the geophysical model measurements and all these, for instance, earthquakes, which are being recorded before the eruption, several days before the eruption, as it was the case for the previous one, if you remember. There were thousands of
swarms.
Yeah, exactly. But the main problem is that we completely don't understand how this magma, we know how the magma forms, but we don't know when is the critical time that this magma can reach the surface and therefore form a volcano. And in the case of Iceland, we are still having trouble with that. We don't know that basically people, they were not really expecting that we're going to have a magma production. And for a very short time, we don't know exactly how the magma chambers in that area are working. Of course, it is one of the best studied volcanic systems in the world, but still, even for these type of systems, as I mentioned, because two main processes are active there, it is making complicated to know that how much magma production we have, when the magma is reaching to a critical mass or volume in order to come up. So that's why it's making it complicated. And for the case of a Icelandic system, as long as I know, because for the new one, at least, they were not really expecting it to happen, but then it happened, and now people are going through the observations, previous observations, to just see that what's going on, what has happened there, and why we started to have this new wave of volcanoes. Basically, probably it will continue, but more observations are necessary, are needed. Observation related to the volcanic eruption itself, but also observation related to the composition of rocks, the magma, because when we study the composition of magma, the geochemistry that I mentioned, we can really see that what is the main source of this magma. We can see that is it related to opening of plates? Is it related to divergent magma production, or no? Is it related to hotspots, or is it a mix of two of them? So chemistry is going to tell us more. And the chemistry work about this volcano are not published yet. There are some works are being done.
Yeah, right.
So more work are needed. And then to compare the composition of these new magmas with the previous one, with the one of last year, and also with the rest of the whole system. And then we can see that what is the relationship and what are we dealing with? Is it something that is a continuum of the previous ones, or no? We have a new batch of magma entering the magmatic system. We need to do more work, in particular in the chemistry of these volcanoes.
I mean, you were saying also that it was surprising, this eruption. Was it this last one right now in August that was surprising, or the first one? Because I couldn't understand if there was an expectation of this already happening, that all of this was going to start going off, or if it was just, it did seem like, they weren't expecting a second one so soon.
As long as I know, the second one, they were not really expecting it. They were expecting something to happen after the big one, after the previous one, but like it just happened like out of nowhere. So it complicated the things now even more. So it's getting even more complicated, especially because people are thinking about that. As I mentioned, a new batch of magma is being entered to the system, so it's making prediction
everything complicated. Yeah, and that was. For someone like me who's not a volcanologist, I was really surprised that in some of the geology groups that I follow, and even the groups in Iceland that are full of volcanologists, geologists, no one really knew. And like you said, I mean, there was a swarm of earthquakes that started about a month before the eruption. And, and then just a couple, I think I had told you I was looking at the graphs the night before it erupted, because I was going back to the US and I wasn't sure if something was about to go off. And it looked a lot like the signature of last year, but I was kind of surprised that, I mean, fair enough, tectonic plates are what? The theory of that is 50 years old or something like that. It's extremely recent.
Yeah, it's almost it's early. It's more than that. I mean, the original from Alfred Wegener.
The original theories,
Yeah, it goes back to 100 years ago, more than 100. But the modern one, it was like
it's recent, right?
Solidified in 60s, and
And that's, I guess it's it's so astounding to think that we can't we have all these active volcanoes, obviously, already that have been studied, and volcanology has existed for some time, but we don't have a notion of where it's going to go off, really, or when it's going to go off. Like, it seems to someone from the public, I would think that's quite scary, that it almost seems like we don't really know anything. We don't know how long it's going to last. We don't know where it's going to go off. They had some ideas at the time of, well, they thought it was going to erupt, the first one near Mount Keilir, and it is quite close to Mount Keilir, but they didn't, nothing. And in fact, the fact that this one erupted so close to the previous one also, it's, what is it that we're missing to understand kind of the full picture? Is it just more data, or is it, how do we predict these better?
It's a very interesting question. The thing is that it's very well known for volcanologists is that we cannot really see volcanoes. We cannot generalize the behavior, the eruption behavior of a volcano. The fact is that you have to see volcanoes, each of them individually. Right. Each of them, they have their own behavior, and that makes the things complicated. Mm-hmm. As you know, for instance, if we're talking about the eruption of a volcano, there are several factors which are affecting that. There are several important factors depending on the origin of this volcano, which is controlling the composition of your magma. And as you know, depending on the composition of magma, how much silica it has, how much gas it has in it, all of these guys are going to control the explosivity of this volcano. So basically, and since each volcanic system, it has its own chemical characteristics, which in consequence, it's gonna also define its physical characteristics in the case of volcanoes, let's say the eruption style. And when we have different chemistries, of course, it's gonna, when we have different composition of magmas, of course, magma is gonna behave differently beneath the surface. And when it behaves differently compared to each other, it means that the prediction of the eruption is gonna be more complicated.
Because obviously there is, can every volcano either have the capacity to be pyroclastic or be these kind of small localized magma flows? Because I think Eyjafjallajökull, the one from 2009, that was a pyroclastic, right?
It really depends on the composition. It really depends. For instance, also it depends on for instance, if you have a volcano, as you know, we have different, as I mentioned, different composition of magmas. The ones who have a higher silica content, the ones who have more volatiles in them, they tend to be more explosive, of course. They will be always explosive volcanoes. They are the most dangerous ones. They are the ones that form all these percolastic deposits, and they are explosive. For instance, the ones that we have in places that two geological plates, they converge, they collide each other. These are the volcanoes that usually form in these areas. These are the dangerous ones. But when you come to the volcanoes which are forming in the divergent areas or in hotspot areas, the magma itself, usually it has very low silica content, usually basaltic in composition, lower volatile amounts, and usually these volcanoes are very, very, they're not as wild as the other ones. For instance, they are similar to the ones that we have in Iceland, the ones we have in Hawaii. Usually the temperature of the magma is too high. It means that its viscosity is going to be lower. It means that it will be less explosive. But sometimes these volcanoes also, even with the magmas which have magmas that we are not expecting explosivity, they can also become explosive. For instance, if they come in contact with water, it happens a lot in the Iceland. It happens as well. That the magma completely came in contact with the ocean water, and it causes explosion. That is one of the cases that is not even though we have a composition, basaltic composition, but we're not expecting explosivity. But if it comes in water,
and I guess
cause explosion.
Because Eyjafjallajökull was underneath the glacier, and now I understand better about why they were so afraid of last year Fagradalsfjäll. It was essentially edging towards the shore, and they were very worried of what was going to happen once it did. And yeah, I guess that then it reaches the qualities of becoming explosive, and so they can actually change states of sorts in that way.
Yeah, exactly. It's so we were just talking. Like a while we were talking about magmas. We saw that we talked about the temperature of the magma. We talked about the silica content of magma, the volatile amount of magma, if it comes in contact with water. So in a very short discussion, we talked about four main factors which are controlling that, and these factors, there are tens of factors.
Yes.
It's
right.
not as simple as that. It depends on the geology of the area, how this magma is reaching to the surface, how, if we have under the surface, if we have the water below the surface or not. This is one of the things that usually helps for explosive volcanoes. So several factors that most of them are unknown are responsible for this basically difficulty in prediction of volcanic activity. Exactly.
Yeah. No, it's, I mean, it must be frustrating for the people of Iceland, because, you know, it really is something that I did not realize until I started, I guess, chasing volcanoes of sorts, which is, the predictability. And I feel terrible for actually a volcanologist friend of mine, whom I met there last year, Yoram. I should introduce you one day. He just left to go there a couple of days ago, and he had booked his ticket when it started erupting. And by that point, I think all the Icelandic experts were saying, oh, this is, the flow is double what it was last year. This one is going to last quite a while. And no, that didn't end up happening. And I feel terrible for, I'm sure it's great for Iceland and their tourism, but terrible for all the researchers and all these people. It's, it's beautiful, and I guess it has less of an interest to active research once it's no longer actively erupting. But in fact, I was going to ask you, I should show you this picture of I flew over the old crater from last year. Let me see if I can share my screen. There we go. So let me share this. So this is last year's crater, which I flew over.
Oh, wow.
And it's just amazing. The colors. And again, this was erupting up until September, I think it was last year. It erupted for 6 months. And I had shared on Instagram some photos of it in the morning, where it was just, the whole field around it was completely smoking. And I kind of wondered, in how long can we go walk on it? Selfishly, I'm wondering, there was a guy last year who actually, I bumped into him at the Blue Lagoon. I can't remember if I told you this. He climbed up to the caldera while it was erupting. Insane. I found his social media, and there were videos. I don't know if it was a GoPro or I think it was just an iPhone. He had climbed up to it, and then lava starts spewing out, and he's just, oh no, I better get out of here. And there's literally an ocean of magma coming towards him. But I kind of wondered, other than the danger of obviously, lava tubes falling into a lava tube, in how long. And again, this might be something that no one knows how to predict, but in how long do you think this is the kind of thing where you can just go up to it as a tourist and, have a look at it inside the crater?
Until magma comes back again, or no? You mean that?
When will it be considered fully safe?
Oh, it really depends on your definition of safety, of course.
I'm probably not a good person.
It depends. Some people they are probably even afraid to go now.
Right.
But some people they've been going while it was erupting. But but I don't know. Honestly, I have not been that close to when it's still active. I prefer to not go that much close to magma. But of course, it's once you know the behavior of the volcano, kind of, you can see that where is it risky and where it's not risky. But it's still always there's
always a risk, right?
Because the magma which is coming up, you have no clue how much bubble of gas, for instance, it has. It can have a very sudden explosion, a small scale, and then it can cause the rim to collapse, or just shaking of the area, and you can fall somewhere, or it can it can release gases which are not good for human body. So it's I would say it really depends on the volcano, and then when once you know the behavior, kind of, you can just do the risk. But people, they prefer to not do that much risk.
Yeah, that's fair. Would you say that I would guess that tourists are probably taking a lot more risks than researchers, probably, right?
Yeah, researchers, because they want to study more volcanoes in their lives. So
they don't want to have short lifespans. Yeah, it's very sad. What obviously, I'm guessing that the I haven't seen. Have you seen Fire of Love, the movie?
I watched it 2 weeks ago.
Oh,
Yeah.
cool. What did you think of it?
I really liked it.
Yeah.
I really liked it. I really love of course, the story of
craft couple.
Craft couple, very nice. And
I should interrupt you to say, for people who don't know, they were a couple of French geologists, volcanologists, active. Both of them were volcanologists. When were they active? In the 60s?
No, it was
80s?
80s.
Yeah. That's why there's such good footage. And they took a lot of footage, and they were unfortunately killed by a pyroclastic explosion. Where was it, in fact?
It was in Japan.
Wow.
Yeah, it was in Japan. I forgot the name of the volcano. And because of there was a no ardent or a pyroclastic flow just came, killed them. But the movie is very good because it is showing a lot of very, very high quality
footage.
Negative footage. Yeah, it's really nice. Quality is very good, but also it shows their story. If you want to see how people, they can get closer to while it's erupting, just watch that movie.
No, I probably should.
Yeah, there is one scene that they go to Nyiragongo, in I think it's called Nyiragongo, the volcano in eastern Congo, next to Goma. They go there, and then you see this crazy caldera similar to this one, but like way more bigger in scale. They reach the top of the mountain, and then you have the caldera.
Yeah.
They are in the rim of the caldera, and then to the bottom of the caldera that you have still eruption there, like half of this place. It's like 200, 300 meters down.
Wow.
So they just stay in the rim of this caldera.
Yeah.
And while you're watching that, you're almost shaking yourself. And then they decide to go down. They decide to go to the bottom of the caldera.
Yeah.
They go there, they go next to magma, and then they decide to camp there for 3 weeks.
Yeah, there were people at the volcano camping.
Yeah, so they were like in the bottom of the caldera, not the top of the mountain. Like,
yeah, right.
The top
just
of
like
the mountain, and then inside on the floor. And they actually, after 3 weeks, they leave because the lavas are just are taking over the whole bottom of the caldera. So they see if they stay like for several hours more, they will just
die. Yeah, I mean, that's.
Well, it's incredible. Very nice story and very nice footage.
I need to. I have plans to watch it, and especially because I think the craft couple, when I was growing up, they were certainly talked about, and their footage was around. And I think, I don't know if they were the first to really get that kind of footage. I think they were.
Probably they were because especially because the quality of the footage, it's very good in a sense that first of all, they knew how to work with cameras, but also they were scientists, so they knew what to capture.
Yeah.
So that was a good thing. So they knew what to capture. So everything you see, all the frames and everything, you can see that they know what they're doing. So I think they were one of the first and one of the best.
Yeah, that's true. I guess we don't talk a lot about. There was a man in the tornado chasing community. I posted about him. He was called Tim Samaras. He was unfortunately killed by a very large tornado many years ago. But he was a person who was a researcher, and because of that, I think he had more interesting documentation than, I guess, for some of us like storm chasers. What we're documenting is probably not that interesting. I think my friends document interesting things that are made, then they may contribute to studies and things like that. But it's true that if you are a scientist who, I guess, has a capacity to handle media and et cetera, then you know exactly and what to document, and that hopefully serves the entire scientific community. I mean, it's interesting because obviously I feel like geology, much like astronomy, has this issue of, well, maybe issue is not the correct term, but I have a lot of sympathy for you guys because you're probably the only other field where I feel things happen over just millions and millions of years. In astronomy, it's kind of the same problem. And even missions, at least maybe you guys have less of the frustration of missions and things like that. But for us, a probe will be planned and then it launches 25 years later, and then it takes, 20 years to get to wherever it's going. And it just, the time scales are so enormous. And I know that you guys talk about epochs and eons and eras. It, is an eruption kind of the most exciting process for geology because it's such a quick, sudden process?
But I will also remind you that the time is
We'll cut it.
So to answer the question, actually, it's a very nice question, but let's not forget that those people who are working with the data coming from probes, especially the space missions, they are more than probably half of them, they're geologists. So
that's true.
People who are working on the return samples, and all of them, they are all geologists. But of course, we are dealing with the very long time frames. At the same time, we are dealing with something like volcano. We are dealing with something like impact cratering, which is even faster than volcano. You have a formation of, for instance, an impact crater 100 kilometers in diameter in less than 2 seconds. So it's really crazy sometimes when you compare different geological processes which are happening, at least their pace, the way they happen. In the case of volcanoes and impact cratering is super fast, and in the case of, for instance, sedimentation, it takes millions of years,
right,
to form. But at the same time, we use these present phenomena like volcanoes in order to understand the past. We need to study these type of volcanoes which are happening in a very short time scale in order to understand the volcanic rocks, for instance, from 200 million years ago, and then we can learn about the eruption and all that thing. But at the same time, it's a very fascinating field, I would say, to just comment on that, because depending on your interest, you can work on very long-term processes. Or you can work on something which is quite happening very fast.
Shorter terms, yeah. What are there other shorter term processes? Let me switch over to a different. We were just talking about shorter geological events and the fact that obviously, there is things like eruptions, even though I understand that they're not necessarily shorter. They inform our understanding of long-term events. What are some other shorter term events that are important for geologists or inform our understanding?
When we come to processes that they happen on Earth, we can say we have high temperature and low temperature processes. And in the case of high temperature, for instance, as you mentioned, volcanic eruptions or impact cratering. And then when it comes to low temperature processes, we have a lot of them actually that can happen in a very short time, but they are geologically very important. For instance, floods are very important, or any type of tsunamis, for instance. These are important because we can track back the tsunamis, floods, and everything related to this type of actions. We can see their sediments. We can see, because all of these processes, different processes, they make the type of sediments which are characteristics of these processes. So when we go back to time, when we study the rocks, when we study the sediments, we can see that yes, in this time there was a flood happened here. So these are the ones. Or like earthquakes. These are one of the other processes that happen in a very short time, and although they can be tracked in the sediments and in deposits, thousands of years later we can track them. So the list goes on and on. So there are a lot of different these type of processes that can happen, sudden processes that can happen on Earth.
Is the West Coast, for that reason, the West Coast of the US particularly interesting because of its propensity for earthquakes and things like that?
That's one of the reasons that you have a San Andreas fault system there. So it's a very interesting for geologists. That's why also it's one of the places that geophysics, basically the science of geophysics, has started. It has a very strong base in western coast of United States. It's one of the main reasons because of the earthquakes that is happening there. So basically, every country that has a geological processes, it's that state or that area is going to be very active scientifically. Yeah. In the case of, for instance, geophysics or earthquake studies or volcanic eruption studies, Japan is very famous, for instance. Or when it comes to different states of the United States, for instance, for volcanic studies, Hawaii, they are very active in that case. Right. But when it comes to earthquakes, as we mentioned, California or that area. So it really depends on because it really also depends on the needs of that country, of that society. Sometimes in the case of at least geology, the budget goes to places that has application in that area. So if we are, for instance, if you are in a country that depends on mining industry, of course, the whole geologist, the focus is going to go to mining, of particular mining, or if you're dealing with earthquakes, it's going to, so it continues, the list continues.
Is anyone allocating more money towards meteorites?
No, because they don't give you, they are one of the areas of science which are like exact science, let's say, exact science in the sense that they don't produce money right now, or they don't prevent danger right now.
Right.
So that's why the money compared to the other parts of the geology, it's very low. Funding is very limited, which is understandable.
Yeah, it's certainly, I'm sure it's frustrating for people who work on meteorites, and sometimes it does. I think I had mentioned to you, my friend Oriane, she works on tracking the parent bodies of meteorites because then they can predict, obviously, impacts on satellites and things like that. And so I can understand that would be something that is worth a lot of money to invest in. But meteorites themselves, once they're down on the ground, less of an interest for the general public, in the same way that it actually surprised me to see statistics on what people want NASA to use money for. Actually primarily goes to people primarily wanted to do research on climate change, near Earth orbiters, so dangerous asteroids and things like that. And there seems to be actually relatively scant interest from the public on lunar landings and going to Mars. And those are things that I guess are interesting for us in the community, things that are like geologists are obviously interested in meteorites, and we're interested in going to the moon and things like that. But the general public has more, I guess the general public in a way reflects the interests of industry and what they want their investment or tax money to go to, right?
That's right. Yeah, I completely agree with you. But even when it comes to the case of meteorites, the fact is that one of the main parts of meteoritics, one of the main reasons that we do meteoritics, we do meteorite studies, because, as you mentioned, near Earth objects, it's because if we want to understand the structure of these near Earth objects or any other asteroids, you need to study meteorites, because these are the samples which are coming from them. If you understand the physical properties of meteorites, it means that you will understand the physical properties of asteroids, and then you can prevent any type of impact. You can predict that what is going to happen if one of these guys is coming towards Earth. Can we go and destroy the object? What type of material we need to destroy it? What type of method we need to use? So that's why meteorite studies
does inform other parts.
Yeah, exactly. Or like, for instance, in the case of space mining, all the knowledge that we have about space mining, we're thinking about extracting the material from the other asteroids or other objects in our solar system. the majority of this information is coming from meteorites, because we know the composition of meteorites with a very high precision, with a very high accuracy as well. So based on the studies that we've done on meteorites, we know that what type of elements are abundant on asteroids, which can be used in the future for economic reasons. So
there's a company in California that does that. It's a fairly recent company. I forget their name, but someone was mentioning it to me recently, or at least they're an actually funded startup on Is that real? Is that, I always wonder how realistic that is, because they always talk about the costs of it being so enormous that how could we possibly, is this, a distant future plan, or is this something realistic that we could actually do?
There are several companies as well. Like it's interesting that one of the main places that this type of space mining companies are active is in Luxembourg.
Oh, really?
Wow. And even the government has funded them. But if it's realistic or not, not really in the short term. Because the type of material that we have on asteroids, it depends on the type of asteroid. So
which we don't know unless we do massive amounts of research.
Yeah, we know that some of them, they have probably they have ice that can be used. Probably we know some of them, they can have some elements that are rare on Earth. But in general, if we need material to bring back to Earth, it doesn't make sense, because we have everything. I mean,
and the cost of it is just
but if we
just seems really prohibitive.
That we want to make stuff up there without taking the material from Earth, that is something that needs a lot of work, needs a lot of thinking, how to process the material and stuff. So it's possible to do. Probably it will be done in the future, but I don't know. Maybe
probably not anytime soon.
No, maybe next 200 years.
Yeah. Did you follow anything of the DART mission? In fact, I think it's happening in about 20 days. They're trying to deflect. They have this binary asteroid that they're trying to deflect a little bit, change, I think, the orbit of one of them in a way that just to test out the technology of doing that in the future. And it's true, I hadn't considered the fact that all the research we have going into meteorites is what informs how we could do something like this.
Exactly. It's so interesting that I have not followed the mission very close, but in 3 weeks ago, I was in the annual conference of a meteoritical society, and I was talking about this very weird type of iron meteorite, and one of the main responsible scientists of DART project, actually, she was very interested in the meteorite that I was studying. So they were really thinking that because it was a new group of meteorites, it had a very unknown or very newly known, let's say, physical characteristics, and it was very surprising for them and very interesting for them that what happens if the asteroid that we are gonna have in the DART mission, it's something related to these guys that we have no clue. So it's a very interesting project, but of course they have used a lot of data, a lot of knowledge from the meteorite science, and the leads of this project. You have a lot of meteorite scientists in the field.
Yeah, hopefully. Is there anything else that you would like to actually see more investment in terms of, obviously I think about meteorites as an astronomer, but are there any other fields of geology and cosmic chemistry and that would deserve more funding? And certainly, like what you point out about the DART mission, I think is actually an amazing way to say we should be funding more research into meteorites and meteoritics. And so is there anything else that I'm sure there's obviously in all sciences, there's lots of fields that are critically underfunded, but are there any specific ones?
Well, when it comes to geology, it's really, you have because it's a very diverse field, as you know. So it really depends on what type of geologist you're talking to. If you're talking to, for instance, when you're doing in geology, we say economic geology, that also I'm active in. If you're doing economic geology, of course, you're going to have more funding because it deals with the mining, it deals with the extraction of new material which are needed for our society, which are needed. A lot of them are critical for
computers, etc.
yeah, moving towards a renewable energy production, and these are extremely important. But usually for these type of things, there is money because it is dealing with the society directly. But then when you come to the other parts of geology, of course, when you talk to, for instance, the paleontologists, they always they're always complaining that there's a lack of money.
Yeah.
Lack of money. And it really depends. It really depends on the field of the geology. For cosmic chemistry as well, always there is this problem of lack of money for space missions, which are necessary for cosmic chemistry. Hopefully, in the future there will be more money, but basically, all the concerns that the cosmic chemistry and meteorite community they are the same concerns that the planetary science community they have regarding space missions. The fact that there is not enough money available to do research, there is not lots of projects which are supposed to be done, they are not being done because of the lack of funding.
Yeah, and that's, I mean, across, I think certainly, you know, I don't know if you saw those articles in Nature and things like that, where they talk about, you know, people don't want to be postdocs anymore. And that's understandable. And there's A, the lack of funding, B, the changed expectations and everything that's expected out of postdocs and researchers. And yeah, it's hard, and there's very little funding, and I can understand that. And I don't know how we, you know, part of the reason I do the things I do is because I want there to be more funding in science, and I want the public to care and to understand how valuable science is for society. But yeah, that's, I think we're all trying to do that, right? You had told me going back to Iceland that Iceland was the geologist's paradise, and in fact, I don't know if they themselves fund a lot of geology research there. I would presume that they do. And I guess, you know, you haven't been to Iceland yet, right?
I have not been in Iceland, unfortunately. Yeah.
You will have to go. And certainly when you're there, I can every time I've been there, even 10 years ago, before I'd heard you say that to me, you know, I understand what you mean, because it's so otherworldly. And then there's also the fact that there's very few trees there. They are trying to reforest parts of it, but I guess, you know, it has a very otherworldly quality to it. And then there was this story that I had shared with you of NASA actually sent 35 astronauts to train there between 1965 and 1967 because of how moon-like the terrain is, which is wild to think that there's a place on Earth that is similar-ish. And they used to play this game that was called the moon game, right? Where pairs of astronauts had to pick up rocks that they thought were interesting. And I don't know how much training, most of these people were pilots, and, you know, obviously they had a very large knowledge of science, but they were primarily, I think, pilots, some of them, the first generation. And then they had to pick up these rocks and give their reasoning, and geologists would look at the samples and award points for the most varied samples. What are the similarities, you know, between Icelandic rocks and lunar ones, for example? How would training there, I mean, I know it's an otherworldly landscape, but how would training there actually help a person maybe understand or get a kind of basic knowledge of what to pick up on the moon?
It's a very interesting question, because when you're dealing with Iceland, as you said, for instance, the lack of vegetation, at least in some parts, probably it's going to be similar to what you see on the moon as well. But at the same time, I think one of the main reasons that they worked there was if we want to compare the type of rocks that we have in Iceland and the moon, they are very similar. Because Iceland is mostly covered by basaltic rocks, at least in the places that you have these volcanic eruptions. And it's the same with the surface of the moon. The majority of the surface of the moon are basaltic rocks. Yeah. As you can see, the lunar mirrors, they are just layers of basalts. And but the fact is that just the only difference is that the ones on the moon are way more older than what you see in Iceland, which are extremely young and extremely new rocks. And so I think they can be the main similarities. the type of trains, the new volcanoes, the type of lava that you have, lava flows that are solidified in Iceland, probably it would be a reminder of what you see in lots of regions on the moon. But of course, also there are differences between the type of rocks that you have there. The rocks that you have on the moon, usually the surface of the moon, most of them, they are completely fragmented. We call them brecciated there because of the continuous impacts of micrometeorites and meteorites and asteroids on the surface. All these rocks, they are broken to pieces, and it's a bit different than what you see in Iceland.
Yeah, because on the one hand, I guess in Iceland you have these very, very active erosion processes of, obviously these the tectonic plates and the volcanism and the ice, etc. But on the moon you have all these impact craters. So I would guess that's also where you have that distinction then of, well, the differences in how those rocks, their kind of lifespan and the crust of it, basically.
That's right. So basically, you have differences, of course, and you have similarities as well. But for the case of lunar missions, they had chosen Iceland. They had chosen a meteor crater in Arizona. They were also doing training there because
of course.
Yeah, it's an impact crater that they were working there. So they were trying to work in places that are going to be similar, at least geologically, and also they are not as complicated as other places. So working in Iceland as well, it's an area with volcanic rocks, and I would say for a non-geologist, it's quite easy to work. Even for a geologist, easy to work because everything is, as I mentioned, it's very fresh, very young. You see the lava flows easily. You can see that, okay, these rocks, they are formed from this volcano, but it's not the case for instance, old rocks. That is very complicated to interpret, even for a geologist, let aside a non-geologist. So that's why I think that was one of the reasons that they had chosen Iceland to do this type of work. Yeah.
And it's funny because now they're saying how similar it is to Mars. And of course, there's talks of, I'm sure you know this, of the idea that we might live in lava tubes when we're on Mars. There's obviously very little protection from, there's very little magnetic field protecting Mars and atmosphere. And so there is this idea that we could go live in the lava tubes that are down in Mars. And certainly parts of Iceland, again, because I have not been to Mars, but parts of it are also foreign in a completely different way to these lunar landscapes. There's obviously also all the kind of geothermal areas where the colors, just the sulfur and everything, are actually, I would say, more reminiscent of Io, perhaps, the volcanic moon of Jupiter. That reminds me of that more so than Mars. But what are the similarities then between Iceland and Mars, if you think of it as, is Mars quite similar to the moon? Or are we just talking purely about the lava tubes that you would have underneath them?
Again, when it comes to the lithology, to the rock composition, again, Martian surface, you have a lot of basaltic rocks.
Right. Yeah.
So these are the main things which are actually, when you have basaltic rocks, which means rocks with lower viscosity, high temperature, it means that you will have this type of lava tubes. And this is the same thing that you have in Hawaii as well. So these type of lava tube formations. And of course, it's a very interesting scenario that in the future we can go and try to stay in the lava tubes, which are going to protect us from the UV light, from all the cosmic rays, solar flare material, which is bombarding the surface of the Mars all the time, and it makes it inhabitable, basically.
Yeah.
But when you go there, it's going to protect you, but also it's going to protect you from possible storms that you have on the surface of the Mars. It's also kind of is going to protect you from the day and night temperature difference. Of course, it's going to be more stable environment. Right. So there are a lot of factors that are making these type of lava tubes or underground tunnels on the surface of the Mars a much better environment to stay there. It's also the case for the moon as well. In the moon also we have lava tubes, but the ones in Mars, they have gotten more attention, particularly because they
Sure.
might be places that host possible life forms.
Yeah, that's actually, I was going to ask you, it's cool that, you know, so much of my field is looking up, and so much of geology and all those fields is, once you get to this place, the moon and Mars, it's looking down at what you have. And that's kind of the goal. We are looking up to then look down at what we have, right? And so what is, obviously, yeah, we all want to find traces of life somewhere. And I'm guessing the Holy Grail is water on Mars, and there's constant back and forth on traces of water. And we know Mars had water in the past. What would be really the most exciting thing to find there something that we can only find ourselves? So something that would be harder to find with a rover or the kind of missions that are there now. What is something that would be just, you know, extremely exciting to find there?
Finding life, I would say.
Yeah.
Just finding life itself. Because we, as you mentioned, in the case of Mars, we already know that in the past of Mars we had liquid water. We already know that.
Yeah.
And also we know that right now it's also liquid water. It's you have it on the surface sometimes.
On the poles especially.
In a short time you have it, and then you just you have the brine deposits. You can see that you had water in this surface for like last month and we missed it, but then you can see the deposits which this water is leaving behind, a lot of salts or a lot of other material.
Yeah.
So it means that below the surface we are having liquid water flowing in some places. Sometimes you can see it represented on the surface of the earth, of the planet. And
alluvial fans, for example, and that kind of thing.
Yeah, these are the ones that the alluvial fans as well. Sometimes they appear, sometimes they might be related to the ice activity, but also sometimes they are related to water. But we can see that they are very recent. So recently they are really active, these type of things. Yeah. But the problem is that, but the exciting part is that probably these lava tubes that you were mentioning, these are the places that the water can be more stable, not immediately evaporate and leaving the surface. So probably there are places that the pressure is good enough, that the temperature is good enough that they can stay there for some time, and the life can survive there.
Yeah, that's true. Obviously, yeah, what you're saying about
just a little bit of water and the type of life which we know on Earth as well, extremophiles, the type of life that just likes to live in extreme environments.
Yeah.
Probably there are some places that this can form. Even on the surface of the moon, it's also possible. But Mars, it's
tardigrades on the surface of the moon, maybe.
It has a more possibility, and hopefully one day. So when you mentioned that what would be the most important discovery, I would say just the discovery of life itself, which is going to be difficult to be done by robotic missions. Probably humans need to be there to look for them.
Would we possibly find stromatolites? I know those are kind of controversial, the older ones. I guess I should probably let you explain what the stromatolites are, these old formations that are, what, 4 billion years old, something like that?
These are some of them. These are the first. They are younger than 4 billion. But like these are the one of the most well-known traces of life in the past of Earth. These are the basically type of sediments that form because of the activity of algae and some microbes together, and then they just form deposits of usually limestone or something similar to that, calcite. So basically carbonates. It's better to say. So these are layers. I forgot to bring a piece of stromatolite actually.
Oh, I should have saved a picture of one, but I'll post one in comments. But they're controversial, right? I mean, people.
Yeah, right now we know that actually because we can see stromatolites forming right now in Australia. You have present-day stromatolites, and you have them in shores of some parts of Australia and some other parts of the world. So that you can see that the stromatolite is forming right now. It is very similar to what had formed in the past. But of course, the first time that they were discovered, people they were not sure that these are related to our to life itself. People they were thinking that probably it's something completely just something not related
just
to
a process,
life.
a geological process of sorts.
But later works they showed that they are related to life, and they are related to early life on Earth, which has formed in the shore and in the presence of water. And you have it in different layers of the Earth, in different times of the Earth, and you can find it basically everywhere on Earth. That you have rocks of a Pericambrian or a little bit older than that. And finding them on the surface of Mars, I don't think right now people are looking for them. People are looking for way more probably primitive type of.
Oh, interesting. More primitive metallites. Okay.
Yeah, probably it's but if you find them, it would be fantastic. But I'm not completely sure that if on the surface of Mars we had the situation and the conditions which could allow stromatolites to form.
Yeah, I was gonna,
but we know that right now there are traces of, at least on the Earth itself, there are traces of life. We know it very well. And also we can see present-day stromatolites, and they have not formed, they have not changed that much. So they are basically.
No, they're beautiful. I learned about them in astrobiology, and I remember thinking, and they were pointing out how controversial they were, and but they're very interesting, and certainly in terms of interesting places. We've sent landers and probes now to a lot of places, like Comet 67P, obviously, I think was one of the more super exciting ones. Titan, I don't know if you ever saw there was this descent, the filming of this descent probe, the Cassini-Huygens, the Huygens probe that landed on Titan. And Venus, I guess in the, what was it, in the 60s or 70s, the Mariner
50s.
1.
It was, I think, in 50s, no?
50, yeah, in the 50s. It was a long time ago.
It was in the 50s, I think.
Quite a bit. But it
probably.
I mean, it barely.
It was very early days, yeah.
And the excitement that people have now for the moons of Jupiter and the moons of Saturn. And there were plans, actually, I don't know if you know about the JUICE mission that is launching I think in a couple of years, maybe a year or two. And it's funny because I know they hate that name, or at least one of the women I went to, I think she was one of the main investigators, the PI on it. And she was saying that they were hoping they were going to change the name, but they kept the name. And they were originally meant to have a lander that was going to, I think, drill down into Europa and try to sample, but the crust on Europa, I'm sure, is so thick. And there was the issues of contamination and all of that. But are there places in the solar system that you actually would favor more than others for, not necessarily for I suppose for finding traces of life, but for exploration in general, in terms of what they can teach us and how interesting they are? And we talk so much about the moons of Jupiter. And I know that Io, for example, is not a good contender for life, or extremophiles, I guess, but I find it one of the more interesting ones. Europa, of course, and Ganymede, who might have under the ice sheet oceans. But which are the ones that you're kind of hoping we go to at some point?
Yeah, just regarding the previous Venera, I got confused.
Oh, Venera, that's right.
Yeah, so it was the 60s and 80s. You were right. I mentioned 50s, which is too early. 50s was the early days of space itself.
Thanks for checking. Well, I mean, it could have, it was sent so long ago. It's actually wild. They sent this.
About these missions, the ones you mentioned, all of them are very interesting. So I would say, as a cosmochemist, I'm more interested in sample return missions from Mercury and Venus. I know it's not easy to do. Probably it won't happen.
No, I'm glad you mentioned Venus, because I think Venus is one of the more interesting places. People care so much about Mars. Years ago, I went to this talk by a specialist on Venus, and I think he was hoping for samples as well. And he was saying, look, we invest all this money in Mars, but we should actually be investing a lot into Venus. And there was that recent phosphine detection that got some attention.
Yeah.
And there is a mission that's going to Venus, I think, by the Russians next year.
Yeah. There's a mission. Yeah. Right now, since last year, if you remember, several missions they were like decided to go to Venus, and which is very interesting. But
Yeah.
when it comes to exploration, and as you mentioned, so as a cosmic chemist, I would be very interested to have rocks from Mercury and Venus. But I know that it's very difficult because of, in the case of Venus, because of that thick atmosphere, but also for the case of these two, because of their location being closer to
Sun.
sun. It means that it's not going to be easy to take something from there and then coming back. You need
We
to.
have meteorites from Venus.
We don't have any meteorites from Venus. We
Yeah.
don't. And the possibility of having them as well, it's low because
Sure.
thick atmosphere, but also everything that has to eject from the surface of Venus or Mercury.
Yeah.
You have that crazy gravity of sun, which is blocking
Oh,
everything.
sure, that of course.
That's the main problem. That's the main problem. Also, that's the main problem for any type of mission that has to go there to take something. You need a lot of fuel and you need a lot of crazy engineering that I'm not very well aware of.
Well,
But when it comes to other parts, of course, Europa and Enceladus, they are very interesting. Everybody would love to see a microscopic view of the droplets of water from these satellites.
Oh,
to see,
yeah.
is there any life there or not? That can be very interesting. So for me, I would go Enceladus and Europa, and as well as Mercury and Venus. These are very interesting for me personally. Of course, Io, as you mentioned, it's a crazy place as well. But I think it's having
volcano chasing, extreme volcano chasing. One day we can do it, maybe.
yeah, maybe one day, yeah. But there are lots of very interesting, really subjects to study. My favorite right now, it was the one for a psyche mission that the one to study the
asteroid, right?
iron asteroids,
Yeah.
which are very interesting, and because we have iron meteorites that are coming from these asteroids, and if we study them, we can learn a lot, because these iron meteorites and these asteroids, they are fragments of the cores of the early planetesimals.
Yeah, planetesimals, right? Yeah.
So really interesting would be to study them and probably to bring back samples. So Psyche, it was supposed to be to launch, I think September, but it got postponed for a year at least. Yeah. So hopefully it will happen one day. So yeah, a lot of interesting objects to study for sure.
I don't know if I ever showed you, we have a big iron meteorite at work that comes from, it's part of the one that made Meteor Crater in Arizona, and it's a Canyon Diablo. And it is so, I mean, it's so heavy. It's 92% iron, I think. And yeah, it, you know, it is important to tell people about these are all kind of planetesimals essentially. All these little fragments, you know, are super interesting. I wanted to do a little show and tell while we're, I'd like to do a little show and tell right now. So let me just share an image that I actually have the rock here, but it's cool if I show it to you. So let's see. Now let me put this one up. Let's see. Oh, is it showing a new image? Let's see.
Yeah, I can see that.
Oh, can you see a different, what are you seeing right now? The eruption or the rock?
The rock itself.
Okay, cool. Yeah, so you know, there are all these different rocks. I sent you some, so I think you have little samples as well. And I wanted to, obviously it's funny because I was devastated that rock actually broke. A bunch of those rocks I drilled last year, and it was very, very difficult to do. We had this crazy equipment to do it, and even that wasn't necessarily enough. This is actually that same rock right now. It only broke in half. Fortunately, it didn't break into a lot of different pieces. But so this is essentially the rock that's on the image, and you can kind of see it's got all these amazing colors on it, all this blue and this kind of green. The one here, it's a bit like that crater, the picture of the crater from last year. It's got obviously all this, you probably can't really tell, but with this light, but it's got red and different colors, and I think you can tell on the image. And then there's also, you know, this one I guess kind of shows also all the kind of alveolus inside And this, yeah, I mean, they're beautiful rocks.
Yeah,
It's really, my stepmom is a sculptor, and so she has always cultivated a love of rocks. So we have so many rocks around the house, everything from marble to serpentine to, so it was actually cool. She was very interested in seeing all those rocks and the colors of them. And a friend of my father, I think I had mentioned to you, has a company where they make tiles from volcanic rock, because I guess I was surprised by how hard they are, but at the same time, when I was drilling into them and I broke a couple pieces, and it was a strange kind of tension in them where they are extremely hard, but at the same time, they're kind of breakable.
yeah, they are glassy.
They're glassy, and it's funny that you are next to them, and it sounds, when you hear the lava moving, it sounds like thousands and hundreds of windows just breaking, of
Wow.
glass windows. And then there were the bits that I wanted to show as well, that were the bits that I extracted, that were those, those were dipped in water,
Yeah,
which creates obsidian, I guess. Is that what it?
yeah. It's let's say it's a volcanic glass.
Okay, it's volcanic glass.
Volcanic glass.
And it was still warm when all of these were still warm when I collected them. And so that one is they're all fresh lava. Some has just been put into the water and crystallized. And there was that third piece that I should probably actually put up now. Well, I'll leave it up to that one, and I'll leave the Tephra for the end. What is you told me that they crystallize, obviously, when you put them in the water. And how does that make them more interesting for analysis? Or I know that obviously the amount of crystals, for example, you have in them will tell you how deep the magma comes from. Is that correct?
It can be actually. So basically, as you know, for rocks, for igneous rocks, the rocks that form as a result of crystallization of magma, one of the things that we can use to classify them is based on the grain size or the crystal size. So when you have a composition, when you have magma, when it starts to cool down, you will start to have different minerals forming depending on the composition. And when the main basically seeds of minerals, they start to form, depending on the rate of the cooling, you will have different sizes of minerals and therefore their crystals.
Yeah.
If you have a rock which has formed as a result of very, very slow, in the matter of thousands of millions of years of cooling down of magma, you will have, we call the plutonic rocks. These are igneous rocks which are formed under the surface of the earth, for instance, like granite. These are the type of rocks that you can see the crystals. You can see clearly all these beautiful crystals. Or another rock is gabbro. Gabbro is a rock that has formed as a result of slow crystallization of magma. And then the same magma that has formed gabbro, if you cool it down with way more faster rate, it will become a basalt.
Right.
So a magma, if you cool it down very fast, like in the case of volcanoes, magma reaches to the surface and immediately starts to form crystals, because there's no time, there's not enough time for the crystals to grow, for the crystals of minerals to grow. Therefore, you will start to have very tiny crystals. That is a sign of volcanic rocks. So one of the, for a geologist, when you show a rock, even from 300 million years ago, they just look at it, they say, this is a volcanic rock, because the size of the crystals, the way they are next to each other, that collectively we call this as a texture of a rock. The texture of a rock is gonna tell you that what is the origin of this rock, or like what type of processes has formed it. And then you have one phase which is even faster cooling than a basalt. It means that even crystals, they don't have to form. They don't have time to form. Everything just forms immediately. So you start to have a rock which really doesn't have any crystal structure. So we call them glasses. We call them
Right.
glass. These are volcanic glasses that in the case of volcanic glasses with the composition of basalt, we call them obsidian, the ones that you mentioned. And these volcanic glasses, when they break, they break in a very irregular way, I would say. They shatter, basically. This is what you were also describing.
Yeah.
And sometimes these basaltic rocks that, for instance, from Iceland, what is interesting is that it really depends on where they're coming from. Sometimes in the magma chamber, some crystals, they start to form already. And these magmas, they can bring some crystals which are formed below the surface.
Right.
Or sometimes they can take rocks from the way they're coming. They can take rocks, for instance, from the wall of the magma chamber and bring it back up, bring it to the top. So basically, just to answer your question, depending on the rate of crystallization, you will have different rocks with different names. Chemically, they will be the same thing, but they will be different. And when you have a magma that you want to know its chemistry very well, it's better to just cool it down very fast, because when it's cooled down slowly, it means that different elements, they will go to different minerals. So your rock is eventually going to be a heterogeneous rock compared to the original magma. But in the case of glasses, because it just forms so fast that it's going to be more homogeneous. When it's more homogeneous, it means that it's better for geochemistry, I would say, because it's not, analyzing that rock is going to be more representative.
Yeah, you don't have to analyze every different parts. And in fact, you know, there were people saying that the magma and the sampling that happened was very different depending. For the first eruption last year, there was different amounts of sampling, and it was turning up very different things at the very start of the eruption and later on in the eruption. And I would guess that geologists there and geochemists are actively looking at the different phases. What is, you know, is it always the same kind of interval that you have in between those changes of the kind of magma you're getting? Or is it a fairly regular set period of time that you're getting different types of magma?
It really depends. So basically, it depends on what is happening in the magma chamber. In magma chamber, you will have basically a differentiation happening. So it means that in different phases, you will have magmas coming with different compositions. But it depends on the type of volcano, really. It depends on the type of magma chamber. Sometimes this change in composition is quite fast. Sometimes it's very slow. Sometimes the magma chamber is when you have the magma, if it comes immediately up there without being differentiated, therefore you will have a more homogeneous composition during the time. But if the magma stays in the chamber for some time and then some minerals, they start to form, it means that, and then they will form, they will sink, and it means that the magma which is leaving the system is going to be different than the later magma which is leaving the system. So it really depends on the magma chamber type, the composition. But yeah, usually it changes during the time. And this is one of the things that also you can use to learn that how much is left for the eruption to end.
Oh, of course. Yeah. I mean, it's, all of this stuff is so exciting. I feel that we, mostly because we don't know, because there's so much we don't know, and there's so much to learn. I wanted to show a last little piece that, unfortunately, let me see if, so I have a picture of it. I think I sent you that picture last year. Let me see if it turns up. Has it turned up? It's the Tephra. I actually meant to bring it back this time around, and it's so fragile that I keep getting scared of bringing it on the plane. And so it lives in Paris right now, but it will come to LA at some point. And it's so interesting. And it's, it's basically like a mushy rock. Is it, in fact, I kind of wondered, is it similar to coral? I mean, coral, I guess, is some coral, live coral is mushy. That's what it made me think of. We found it.
Basically, it's a solidified ash, basically.
Yeah.
When the ash comes next to each other and then they're glued to each other, it is forming something similar to that. Very fragile, as you mentioned. And for me, it's similar to the composition of a sponge. This sponge, it's very similar to the type of a sponge texture.
Is it also interesting to analyze? I mean, I know it's ash. And so I should mention that we found it, I found it after I took the helicopter ride last year, who landed us at a little hill that was near the eruption site. And she said, the pilot was saying, oh, there's plenty of those little pieces everywhere. And they seem to be, I guess they're ejecta of ash that has been has gone through some type of process during the ejection. Am I correct?
If it's an explosive phases, it can produce ash. It means that the ash is basically the very fine grained part of the magma, which is basically ash is basically the very fine grained part of magma which is coming up. So if you have more explosive activity, you will have more ash production.
Right.
And the question about if it's interesting to analyze, it really depends on the type of study and the subject and what questions the geologists they want to answer.
Yeah.
Volcanologists, they always study the ash. Always they study the ash because in the past time and also in the present time volcanoes, they study the ash to see that what is making that ash and not like the other magma. Of course, the composition probably it's going to be different, and what's the reason that the physical properties are different and all these things. Usually they study them. Well, actually, most of the volcanologists they study. Volcanologists, for me, most of them, they are the ones who are studying the deposits. So the ones who are studying the deposits like pyroclastic deposits or ashes, rather than people who study the rocks themselves, because the ones who study the rocks themselves, mostly they are geochemists.
Yeah.
And more traditional geologists, I would say,
We did speaking of ash, we did a trade recently at work. I traded a little piece of the crystallized, the glassy volcano, the glassy magma, for a little bottle of ash from Mount St. Helens.
Wow.
So yeah, I was like, is this a fair trade? I don't really know the value of these things scientifically. But actually, it made me think of the Tephra. Made me think of. I think I showed this to you. It's a little tektite.
Yeah, it's so beautiful. I hadn't seen that actually. Wow.
Yeah, it's a really nice tektite that I was gifted. And so I was kind of thinking like, oh, do tektites seemed, I know they're not mushy, obviously, and they're not meteorites. They are also, I guess, I should clarify for people who don't know what they are. They are little pieces of ejecta, right? That or like material from Earth that during an impact from an asteroid or meteorite get ejected into the atmosphere and come back down, and that's why they have this similar kind of crust, right?
Exactly. You described it very well. It's exactly like it's a natural glass, like obsidians that we talked before.
Mm-hmm.
Very similar to obsidians in lots of senses. Very, very similar, actually. Only experts, they can say if it's an tektite or obsidian. You do the chemistry analysis, and then based on the amount of water that you have, you can say if it's tektite or not. Because tektites, they have very low amount of water. Anyway, but tektites are basically the products of the impacts. Big impacts, usually big impacts to the surface of the earth, and then when you have this splash of material, molten material that are going away from the impact crater, depending on the size of impact crater, sometimes they can cover several countries. And then when they come back, of course, the molten material, they take the aerodynamic shape, and they can be spread in, as I mentioned, in several countries. And these are very interesting subjects for study for geologists, in particular meteorite scientists. They are not meteorites, but they are products of meteorite impacts.
Yeah.
Therefore, most of them, they have the traces of the meteorites in them.
Oh, interesting. Okay. Yeah, because I kind of wondered, you can identify, I think some of the big meteorites are identifiable, right?
Yeah, yeah.
by
So,
composition, but I didn't know if tektites, I could probably ask the person who gave it to me where it came from, but I didn't know if you can actually can you identify the meteorite or the area that it might come from is something I don't, that I'm not really knowledgeable about.
so first of all, most of tektites, they can have the trace of their impactor. It depends on the type of that meteorite that asteroid that has impacted. And some elements, for instance, the elements of the platinum group,
Oh, right.
they are so rare on the surface of the Earth, and there are a lot in the particular meteorites.
Oh,
So then it
interesting.
means that in the resulting tektites, you will have a spike of these elements. But at the
Okay.
same time, there are lots of strewn fields, we call them tektite strewn fields on the surface of the Earth.
Mhm.
That some of them are related to already known impact craters that knows that
Right.
we know what is the impact crater responsible for the formation. Usually they use basically location data and geographical data. And then you can see the shape of the distribution of these tektites in several countries.
Oh,
And
amazing.
then based on that, you can see that probably from where they have originated. And then you look for any impact crater in a
Wow.
particular size that could create
That
such
kind of
fragments.
ejecta.
And for lots of them, impact craters are known.
Yeah.
Impact craters are known, and their products are known.
Right.
But also some areas we have we have tektites that, for instance, we discovered. I was also collecting them from the Atacama Desert, type of tektites that the paper was out last year in geology. It's called Atacamaites, and they are in the surface of the Atacama Desert in the northern part. You have a lot of them.
Really?
But their scale of a distribution is not as big as I don't know, like the tektite you were holding, or like they are not that big scale, large scale, but they are spread on the surface of the desert. But still, people are looking for the impact crater that was formed. So it means that there are lots of there are some tektites, there are some tektite strewn fields that their impact crater is not identified yet.
Right.
And
because is there an impact crater? What is the impact crater related to the Atacama?
Oh, people are looking for it.
Okay, yeah, that's what I know. Obviously, we spoke about this. Do you know Luc Laben? He's the French. Yeah, he's the French meteorite specialist. I met him. That's actually how
I have classified a lot of meteorites for him.
Oh, cool.
Yeah,
he's great. He helped me years ago when I was at a big auction for meteorites in Paris, and he was telling me like, "Oh, don't buy this. You don't want this. It's bad." And he obviously goes to the Atacama, and we were talking about this. Obviously, when you are looking for meteorites, you want to go to deserted places. I mean, there's probably plenty of them in forests outside of Paris or Brussels, but how are you going to find them? Whereas if you go to these deserted places like the Atacama Desert or Antarctica, which Antarctica also has, I don't know if you found any when you were in Antarctica or if that was.
Yeah, we had a very successful mission, and we found almost 70.
Oh, wow. Because they have a different formation. I mean, the way you find them there is different, right? Because it's something to do with the ice freezing and them coming back up or something like that.
Yeah, that's right. So basically, we go to deserts to find meteorites, because these are the places because meteorites, they have a different composition compared to terrestrial rocks. In particular, for instance, they have a metallic iron inside them,
right,
which is very rare on the surface of the Earth because of the presence of oxygen on Earth's surface. When you have iron, it bonds with oxygen
oxidizes,
and then it forms the oxides, silicates, etc. It's the same, for instance, with the basaltic, with the magma in Iceland. This magma has a lot of iron inside, but the moment it starts to crystallize, it starts to bond with the oxygen, so it forms different minerals which are basically bound between iron, oxygen, and other things. But in the case of meteorites, they are coming from an environment that there was not enough oxygen, so you can have pure iron. So when these meteorites, they fall to the surface of the Earth, what happens to the iron? It wants to bond with the oxygen of the terrestrial surface. What does it mean? So it means that the meteorite starts to get rusted. It rusts and it gets weathered, and then during the time it goes away. So for instance, if you have a meteorite that falls in Paris, in a matter of several hundred years, it will be completely destroyed. It will be completely weathered and turned to soil. But when you go to desertic areas, the places that you have a lesser amount of liquid water, which is the main agent
Less erosion,
for the weathering, it means that during the time when a meteorite falls, it can stay there for thousands of years. And during the time when all these meteorites they are falling, you can start to have a concentration of these meteorites on the surface of the Earth. It means that the relative abundance of meteorites on the surface, it increases. In desertic areas. For instance, in the Sahara Desert, you can find meteorites that have fallen 15,000 years ago.
Wow.
You can still go and collect them.
That's
and
amazing.
Then you have the Atacama Desert, which is the driest hot desert on the Earth, which is the oldest hot desert on the Earth. And then we have discovered meteorites that have fallen 2.5 million years ago.
Yeah.
It means that when you're there, the surface of the desert is basically the same surface that the meteorite has fallen. Meteorite fallen, stayed there for 2.5 million.
Wow.
And then we go to Antarctica, which is a desert as well. It's a cold desert. But what's interesting about Antarctica is that when a meteorite falls to the surface of the ice, there is no liquid water. So meteorite is frozen inside the ice, and then inside the snow basically in the beginning, and then it goes ice, and then you start to have layers of ice, and it means that this meteorite just goes below the surface slowly and then stays inside intact for thousands of years inside this ice. But as you know, also Antarctica has glaciers. The whole continent basically is glaciers. And glaciers, they start to move away from the top area of the continent, and then they just end up at the end to the ocean. You've seen all these glaciers that fall to the ocean. It means that every meteorite which is inside this ice, eventually it falls to the ocean.
Right.
But some parts of Antarctica, when this ice is moving, it can be blocked by the mountains, which some of them are below the surface of the ice, some of them are seen outside. And then when you have, for instance, this is a mountain here, and this is the ice, which is going its way. And then it can just basically get blocked by the mountain. And then there is a pressure here. It has something is going to happen to this ice. It can't push the mountain, so it just gets pushed up.
Right. Ice
comes up, and then you have all these winds all the time, which is blowing in Antarctica. Katiabatic winds, and then it will mean that it will destroy the ice. The ice will
go away, kind of,
go away, and every meteorite that is inside the ice, it will just stay there on the surface. So during this activity, you will have places that you will have a concentration of meteorites. You will have several meteorites, hundreds of meteorites being deposited there. Because of the activity of the ice. And then when you know how the ice works in Antarctica, you find these places, you know that, okay, if I go to this area, there's a chance that I will find meteorites. And we find those places, and then we go and we collect meteorites from those places.
That sounds like an amazing treasure hunt.
Yeah, it is actually. Yeah. So that's one of the main reasons that we go to deserts. In particular, we go to Antarctica because especially Antarctic meteorites, because also they have not been in contact with any type of soil and other things like that. So they're extremely fresh, and they are basically very similar to the meteorites that have just fallen from space. So they are very
pretty cool.
Scientifically. Yeah.
So Antarctica, Atacama, Iceland, what are parts of the world, other parts of the world that are kind of, I know they're all interesting geologically, but some more than others, I would suspect. And you're from Iran. I don't know if there are any particular areas that are of geological interests in Iran, but what is one place you really want to go to geologically that isn't Iceland? And that is, that's somewhere that has interesting stuff going on,
For me, I would say, depending on your interest in geology, what area of interest you have in geology, this place is also is going to be different. For instance, if you're interested into the the formation of diamonds, for instance, of course, South Africa is going to be
Sure.
interesting for you.
Yeah.
If you're interested in different type of processes that have formed, I don't know, for instance, copper mines, going to Chile is going to be interesting, but in an easy way to let's not talk about all those diamonds, but like geologically
Sure.
active places. Usually we like places that are geologically active right now. And one of my my interest is the Eastern African Rift. It's
Yeah.
the place that basically African continent, it's getting separated from each other because plates are moving. And along this line, you have this rifting system, which is causing the magma to come up.
Hmm.
And that's the place that you have a Red Sea in the north, and then it just continues. It comes toward Ethiopia,
Yeah.
Tanzania, Kenya, and all these volcanoes which are forming along that line. That
That's
is
amazing.
one of the most interesting places that I would like to work and to visit. It's the place that you have a very particular type of magma coming up. It's a place that you have a rifting. It means it's a place that you have you have the continental lithosphere, which is breaking up, and the magma is coming up. So it's different type of magma, and that's my interest. That's
Okay.
one of the places that I'm really interested. And about the geology of Iran, Iranian geology is extremely also interesting because it's a
Mm.
place that two big oceans, one of them Paleothetis and one of them Neothetis. This is the place that these two oceans they get closed. It's the closure place, and we call them suture zone. It's a place
Okay.
that two oceans they closed. It's a place that basically you had two plates moving towards each other, and in the middle there was the
Kind of.
ocean, and
Yeah.
then the ocean get completely closed, and then these two plates they started to push each other, and because of this processes, you have a very diverse type of rocks have formed in the country, and geologically it's a very interesting for everybody, for all geologists, and especially European geologists. They used to love Iranian geology, and they used to go there and work a lot, and
Yeah.
still there are lots of people. Yeah.
Well, hopefully one day we can have more. I mean, again, everywhere is, we would love to, I'm sure, access everywhere for all those things. And probably
Yeah,
why Iceland's been so popular is that it's accessible.
exactly.
Uh,
It's easily accessible. Yeah, exactly. But I
that's
would say it really depends about all around the earth, everywhere. It's really interesting
yeah.
for
Especially
geology.
the differences, I guess,
I mean,
right?
except like Netherlands, that has.
Le plat pays is Belgium, I
I
guess.
mean,
But
like, at least Belgium, we have some funny stuff going on, but like Netherlands, seriously, like, there's nothing. Just
there's nothing.
not,
Sorry to my Dutch. I know many people who are scientists
yeah, I know.
in
I have
Holland, but no, but that's fair. All right, we've
um,
got 10 minutes left, so I'm going to ask you just two more questions.
yeah.
And this, in fact, made me think of Journey to the Center of the Earth by Jules Verne. I don't know if you've read it, but it's one of the few sci-fis that is kind of around. So many of the sci-fis are obviously around space travel, right? Which is great
Yeah.
for us astronomy people. But there's only one I can really think of that's centered on geology, and that's Jules Verne, Journey to the Center of the Earth. Are there, and in fact, there's a mentioned character who's an Icelandic scholar who's named Arn Saknussemm. I'm probably not pronouncing it correctly. But are there some sci-fis or maybe niche ones or that that are connected in any way to geology? I'm trying to, it was hard to come up with some. I looked up and that was the only one the main one I could think of.
Well, all of them are crappy.
Yeah, well, that's totally fair. Hey.
Yeah, very
There's a lot
bad.
of bad space sci-fi too.
No, I mean, like, besides, I think there are a lot of good space sci-fi, but every sci-fi about geology or earth science is just crap. Because it's not what I'm saying is the old geologists, they believe like you have You have a very weird movies about, like, there's this volcano in Miami. There's this magma. There's
Dante's Peak with Piers Brosnan.
yeah. There's like a flood. There's a quake. The San Andreas Fault, I
Oh,
remember.
right, yeah, San
Yeah,
Andreas.
so there are like like you have magma coming out of a sewer system of the city, that type of things.
Oh, there's the LA one where a volcano basically comes out.
Yeah, it's called Volcano.
It's
Just
called Volcano. That's right. Yeah, Tommy Lee
and
Jones.
also I saw there is one I haven't watched. It's Tarzan in the center of the earth. No, Tarzan in the Earth's core, or something like that.
That's right. Yeah, there is. I guess where a strong
So,
and also that meets is
so
empty
yeah.
core, Earth having an empty. I don't know.
Yeah, so
Which
but if so, only geology, unfortunately, they are very bad.
is
But
true. Yeah.
if we want to talk about like if we expand it a bit to expand it or extend it to the Earth, to the space science,
Yeah.
still in space science we have good ones, but also we have bad ones, like we have Armageddon and all that things.
That's right. Yeah, there is. Yeah. In fact, speaking of pseudoscience and all those things, I don't think I've ever shown it to you. I have a geology poster in my house. It's just like an old vintage geology poster that I like. And it has drawings of lots of different rock samples. And I've had people, I live in Los Angeles. And so occasionally I've had people say, oh, I thought you were not into crystals. And it is true that especially, I guess it's not necessarily a recent thing, but pseudoscience has kind of co-opted the enjoyment of having a rock collection, right? Also backing up the prices of all these amazing rocks. And I have strong feelings about things like astrology and astronomy and the confusion of it. But is there anything positive that association has brought to the field of geology, geophysics? Has it been a conduit for people to be interested in geology in any capacity?
I don't think so. I don't think so.
Oh,
Yeah, I wish there was, but I don't think so. The whole thing about the healing rocks and all this thing, I don't think it has brought anything positive to geology. It's probably it has helped uh, for people who want to just extract kind of precious rocks and to sell them.
etc. Yeah.
But probably it has done it, but besides that, probably it has helped people to remember the names of some minerals.
Yeah, that's true. Hey,
But I think the
have gotten it
cons are
geology.
yeah, there are very bad aspects to that, especially when people they take different types of rocks based on their character, based on how they can heal themselves. Like if they have a bad liver, they take like a particular type of rock. So I think the rocks, as we know, they really don't have effects on us when we are keeping them next to, except if you have a uranium ore, like having as a necklace. Of course, I wouldn't do that. But the other type of rocks, yeah.
Otherwise, geologists would be the healthiest, most balanced people in the world.
Yeah, indeed, yeah, which we are not.
Like most people in science. Okay, last question. Any misconceptions about geology that you wish, cosmic chemistry, geophysics, that you wish you could kind of dispel?
I think one of them is just we mentioned about the fact that the rocks have healings effects and stuff. That's one thing, and the other thing would be the very bad view that people they have towards, for instance, mining industry. Of course, we know lots of mining companies they have done bad things, but at the same time, we shouldn't forget that for a future, for with a modern technology, even for a future, if we want to move towards cleaner energy production,
Sure.
we need to extract material from the earth. We don't have enough material to do recycling yet. We don't have technology to recycle it for lots of elements.
Yeah.
So in order to move towards a cleaner future, we need to do mining. But of course, we know as a geologist, we know that we need to move towards a more a mining which is going to be more responsible, we're taking care of all the environmental factors and everything, and hopefully we can
have more, have more ethical mining of some
yeah,
capacity.
exactly, and then we can have a cleaner and more modern future for humans.
Well,
But of course,
yeah.
we have to take care of our planet, and these things have to be taken into account. So I think that was my comment.
Yeah, that's a good optic, and I think that's something that a lot of people don't necessarily think about when it comes to, you know, everything is lumped into one category as mining
Yeah.
is bad or blood diamonds or all of that.
Yeah, because without mining, we couldn't chat with each other.
We couldn't be chatting right now. That's true. It is part of all those things that receive investment for a good reason. Well, thank you so much for chatting, and hopefully we'll have to do this again next time at the volcano. Next time I'll get the best phone network out there, and we can actually chat at the volcano, or you can come. I think I will try to organize a trip at some point, and you will have to absolutely come to the volcano with a group of people, and we can and you can actually hopefully tell us. Maybe we can play the moon game, the moon rock game, and we can collect.
Cool. Yeah, I would love to. Yeah, thank you very much for inviting me, and I was very. It was fun to chat with you, of course.
Awesome.
And yeah, hopefully next time we can do a chat while you're in the volcano, or I can be there and we can see.
Just like the craft, we can go camp inside the caldera.
I prefer to not do that.
Still,
I used to do it when I was like 18 years old, but now I'm very careful.
yeah, no, that's fair. I will at some point. I will learn something will happen, and I will finally have a moment of like, hey, at least I don't walk on the lava. I'm not part of the people who walk on the lava, because there are a lot of people, and I feel, but yeah, it is dangerous.